talk is about creating a nanochannel in polymethyl methacrylate for microfluidic applications. And the work was supervised by Professor Hassan El-Hofy and Professor Ahmed, El-Bab, and the advisor is Professor Yoshino, Masahiko. Over the past few years, there has been a growing interest in the use of microfluidics devices in many applications, like medical, chemical, and electronic among others. These devices use microchannels, which are used in applications like DNA testing, chromatography, and electrophoresis, among many other applications. Now, why are these devices highly demanded and used? Initially, they were made using silicon, quartz, and glass because of the available micromachining technologies and the properties that were favorable, like high mechanical strength, optical transparency. But at the moment, they are using PMMA and other polymers. So these devices are highly demanded because of many advantages that they offer. They process small amounts of samples, and they take short time to do analysis, and they are fabricated very cheaply, and they are able to integrate multiple steps in a single device. So you can do many things in one device at the same time. And also, they have high sensitivity, repeatability, portability, and biocompatibility. Now, why are polymers like PMMA being used to make microfluidic devices? Those are very properties. Polymers have lower cost of application. They have good optical transparency. They are biocompatible. They are cheap, and they are disposable. And also, they have high absorptivity of about 95% in the infrared region. Now, CO2 laser ablation of PMMA is simple, flexible, cheap, and time-saving. But it is so difficult to achieve precise dimensional control. Why? Because of thermal defects, and also the ignorance of the properties of the material changes under different conditions. The defects include melting of the substrate, clogging, heat-affected zone, high surface roughness, and solidification in the ablation zone. What are the solutions? The solutions are to coat the material before fabricating the microchannels, and then to control the inputs like power, speed, pulse rate, and others. This work is motivated by the fact that this material, PMMA, is one of the most prominent materials for polymeric microfluidic applications in use today. Because it has favorable properties, like it is cheap, easily available, transparent, lightweight, it has high strength to weight ratio, it has good biocompatibility, and also it has low heat capacity, among many other properties. Now, what is the main objective of this work? It's to improve the quality of the microchannel fabricated on coated PMMA using CO2 laser. And the specific ones are to investigate the effects of power, speed, pulse rate, and coating of the PMMA with 99.95% pure aluminium on the quality of the microchannels. Number two is to determine the optimum set of inputs, power, speed, and pulse rate for CO2 laser micromachining of aluminium-coated PMMA using response surface methodology. The third one is to model CO2 laser fabrication of microchannels on aluminium-coated PMMA using adaptive monophasic infrared systems. Now, what did we do and what did we not do? We studied the effects of power, speed, and pulse rate on the microchannel with depth, aspect ratio, surface roughness, and heat-affected zone. And we also carried out optimization and statistical analysis using response surface methodology. We also did artificial intelligence modeling using adaptive monophasic inference system. This is what we did. We looked at the work done by some people, which is in line with what we were doing. And then we found Chung and others
coated PMMA with 0.03 millimeter thick metal film made by wet etching using SUS-304 stainless steel in a solution of iron 3 chloride. They fixed power at 1.5 watts and speed at 32.2 millimeters per second. And then they fabricated holes in air and with the metal film, and then compared the results. This is what they found. This is in air, and this is with the metal film. Now they found the height of the bulge and diameter of the hole in air. The diameter of this hole in air was 305 micrometer, and the height of the bulge was 10.6 micrometer. With the metal film, this is what they found. The values reduced. The height of the bulge became 0.4 micrometer, and the diameter became 103 micrometer. Mohammed and others conducted a very interesting study. They varied speed from 5 to 12.5 millimeters per second and power from 2.4 to 6 watts, and they fixed the pulse rate at 1,000 pulses per inch. They coated PMMA with 300 micrometer layer of water. Then they fabricated in air and in water and compared the results. And they found very interesting results. This is in air at 3.6 watts, 5 millimeters per second. Now, this is what they found in water when they coated the material with water before fabrication of the microchannel. And then they were able to reduce heat affected zone from 493 micrometer in air to 142 micrometer underwater. As we can see, the microchannel in air is not so good compared to the one in water. Now, this is the plot of the microchannel width against the scaling speed in water and in air combined. So they concluded that underwater fabrication of microchannels results in smaller heat affected zone, smaller surface roughness, smaller depth, and smaller width, but high aspect ratio. In a progressive study, Mohammed and others conducted multi-objective optimization using the Takuchi method of design experiment. The inputs were 3 watts, 3.6, and 4.2 watts, and speed 15, 20, and 25, and the pulse rate 800, 900, and 1000. This is what they got for surface roughness at 15 millimeters per second. In air, which is the red line, and underwater, this one. Then they performed analysis of variance to find out the significance of the inputs, and they found that power is the most significant, followed by speed, and then pulse rate. They found the optimum conditions for fabrication in both air and underwater to be 3 watts, 20 millimeters per second, and 900 pulses per inch. Now, this is the optical image they found in air, and this is what they found underwater. This is really better than this. Underwater is better than in air. Now, artificial intelligence modeling of the process has been done by many other people, and they found very interesting results. With fuzzy logic, Hussein and others modeled curve width in CO2 Laser ablation of PMMA. This is the curve width. They obtained it by subtracting H1 from H2, then divided by 2. Then you get curve width. The inputs were assist, gas pressure, power, speed, and sum of distance. They are here in this diagram. And then they obtain a relative error of only 3.852% and a goodness of fit of 0.994. That shows that the results were highly accurate. This value of 3.852 is a very good result because in most cases, an error of up to 10% is acceptable. So to get something like this means they really did something good. Now these are the surface plots that they produce. And they concluded that curve width increases with the increase in the standoff distance. At higher speeds, curve width decreases after reaching a peak value. And then increasing power increases the values of the curve width. Ahmed and others in 2015 conducted a very interesting study. They combined response surface methodology ANFIS which we used, and ANN, artificial neural network, to study curve taper and material removal rates in laser beam machining and laser welding of aluminum trioxide metal matrix composite. They produce a very wonderful plot. This is the percentage error for the three methods. You can see that for ANFIS, which is green, the values are the smallest compared to response surface methodology and ANN. This is for material removal rate, and this is for curve taper. Then they concluded that ANFIS, which is what we used, has the best prediction accuracy in both processes. Now, they produce some wonderful surface plots. As we can see, this is modulation frequency against laser power, the wait time against gas pressure, and the pulse width against laser power. Now, what exactly did we do? What was our work? This is the most interesting part. The work was done in three parts. In part one, we did fabrication of the microchannels on aluminum-coated PMMA using a low-power CO2 laser. The idea here was to find out if coating the material can improve the quality of the microchannels. So, these are the conditions. We use power from 1.5 to 7.5 watts, speed from 5 to 17.5 millimeters per second, and we fix the pulse rate at 1000. You may wonder why. Because the maximum value gives the best results. So we fixed it. And we coated with one micrometer layer of aluminum before fabricating the channels. We fabricated in air and with the aluminum, and then we compared the results. And we found very interesting results. This was the work material, measuring 30 by 25 by 6 millimeters, transparent PMMA. And then, using the laser machine, we cut the material. We cut the samples using this laser machine. And then, using the deposition machine, we deposited aluminum layer on top of the samples. Then, using the laser machine again, we fabricated the microchannels. Then, using aluminum etchant, we removed the aluminum coating. And then, using the laser microscope, 3D laser microscope, we did the characterization of the microchannels. Now, in part two, we used response surface methodology to investigate the process. We designed the experiments using Minitab 19.1, and we used 3-level cellular composite design. 18 experiments were performed, replicated 3 times. So in total, we had 54 experiments that we performed. This is the design of experiments. We used speed 10, 15, and 20 millimeters per second, power 1.5, 3, and 4.5 watts. And the pulse rate 800, 900, and 1000 pulses per inch. We performed analysis of variance to find out the significance of the inputs on the responses. And then we optimized the parameters. Then in the last part, we modeled the process using adaptive neural fuzzy inference system. What exactly is ANFIS? Adaptive neural fuzzy inference system combines artificial neural network and fuzzy logic. So we were able to combine ANN and fuzzy logic to model the process. ANFIS follows the fuzzy's if-then rules, which is in the format of if A is X, then B is Y. Pretty simple. Now, we use 3 membership functions for each input and output. And we chose the Gaussian membership function type. And then we use the following equations to fuzzify the process. The first one is for power. We vary power from 1.5 to 4.5. The second one, speed 10 to 20 millimeters per second. And the last one is the pulse rate, 800 to 1000 pulses per inch. We falsified the outputs using the following equations. The first one is for the microchannel width, which these are the results we got. The minimum was this and the maximum was this. And then this is for depth, aspect ratio, heat affected zone, and surface roughness. The experimental procedures. We used ANFIS toolbox in MATLAB 2022A, because it was the latest version of MATLAB at that time, so we chose it. And we conducted 54 experiments, and we got 54 values for each input. And we used 70% of the values for training and 30% for checking. This is the convention in ANFIS. And then we loaded the data with all the inputs, but only one output at a time, because ANFIS does not accept more than one output. And then we produced the ANFIS, the system. We set the tolerance to 0, and 54 training epochs were used. Then we trained the system, and we generated 27 rules automatically from the training networks using the training data. And then we produced the surface plots of the outputs. And then we used Minitab 19.1 to analyze the results. Now, we were able to assess the models using the following equations. Number one, we calculated the absolute prediction error using this equation. And then we calculated the absolute percentage error using this equation. And then we calculated the relative error using this equation. And we were able to get the goodness of fit using this equation. What results did we get from the 3 parts? The work was done in 3 parts, remember this. In part 1, what did we get? It is important to remind you that in part 1, we fixed pulse rate at 1000, and we varied power from 1.5 to 7.5. And we varied the speed from 5 to 17.5 millimeters per second. Now, we got better microchannels on the coated samples compared to the channels on the uncoated samples, as we can see here. This is what we got at 1.5 watts and 17.5 millimeters per second. This is uncoated, this one. Then this is when we coated with aluminum. We got better microchannels. Then this is a 3D image for the uncoated and then for the coated, under the same condition. And then we were able to plot the graphs to indicate the effects of the inputs on the outputs. We started with the microchannel width. This is the plot of the width against laser power. Then this is the width against speed, the scanning speed. Now, at the maximum power and the minimum speed, this is what we got. For the uncoated, the value was 739.005 micrometers. At the same condition, for the coated, the value reduced to 335.215 micrometers, a percentage decrease of 54.64%. Then, at the minimum power and maximum speed, for the uncoated, we got the value to be 322.435 micrometers. At the same condition, for the coated, we got 129.998 micrometers, a percentage decrease of 59.68%. Then the microchannel depth, the plot of the depth against the laser power, and then the depth against the scanning speed. Now, at the maximum power and minimum speed, we got 998.396 micrometers, microchannel depth for the uncoated. Then when we coated, we got 780.325 micrometers, a percentage decrease of 21.84%. Then, at the minimum power and the maximum speed, we got 168.158 micrometers for the uncoated, and then we got 93.066 micrometers for the coated, a percentage decrease of 44.66%. Then the aspect ratio, we divided the values of the depth by the values of the width to get the aspect ratio. Aspect ratio versus power. Aspect ratio versus speed. Then at maximum power and minimum speed, for the coated, we got 2.633. And then for the uncoated, we got 1.451. A percentage increase of 81.46%. At minimum power and maximum speed, we got aspect ratio to be 0.716 for the coated. Then for the uncoated, it was 0.522, a percentage increase of 37.16%. Now, high aspect ratio values are required in high fluid flow applications like cell screening, but low aspect ratios are needed in DNA examination and separation particles among other applications. Then the surface roughness, laser power and surface roughness. Then scanning speed and surface roughness. At maximum power and minimum speed, we got the values for the uncoated sample to be 310.254 micrometers. Average surface roughness. For the coated, the value decreased to 84.692 micrometers, a percentage decrease of 72.70%. At minimum power and maximum speed, for the uncoated, surface roughness was 25.579 micrometers. The value reduced to 9.020 micrometers for the coated, a percentage decrease of 64.74%. Then heat affected zone, the final parameter. We plotted heat affected zone with laser power and heat affected zone with scanning speed. At maximum power and minimum speed, we got the value for the uncoated to be 486.225 micrometers. This value reduced to 328.874 micrometers for the coated sample. Now, the percentage increase is 32.36%. Now, at minimum power and maximum speed, for the uncoated sample, we got 109.163 micrometers. And then for the coated sample, the value of heat affected zone was 77.028 micrometer, a percentage decrease of 29.44%. And then we move to part 2. In part 2, we use response surface methodology to study the process. And we use power 1.5, 3.0, and 4.5 watts, and the speed 10, 20, and 30 millimeters per second. And the pulse rate 800, 900, and 1000 pulses per inch. Now, this is a microchannel profile that we got at 4.5 watts, 15 millimeters per second, and 900 pulses per inch. The microchannel profile is affected by many factors, like the nature of the work material, the speed of the laser beam, the number of the laser pulses, the pulse frequency, power, and many others. Now, we performed analysis of variance to find out the significance of the input. According to ANOVA, an input is significant if it has p-value less than 0.05. Now, this is what we got for all the inputs. This table summarizes the ANOVA results. So, for example, for heat affected zone, power was significant, speed significant, pulse rate significant, but the square of the speed was not significant, and the square of the pulse rate was not significant. And also, the interaction between the speed and the pulse rate was not significant. Now, X represents not significant in this table. So, we then studied the interaction effects of the inputs on the responses. Following the results we got using the response surface methodology, we start with the microchannel width. This is the main effects plot for the width. Now, these results simply confirm the results we got in part 1. There's nothing new here. So, from this graph, we can see that microchannel width increases with power, with the increase in power, but decreases with the increase in speed and the pulse rate. This is the interaction plot for the width. This is the interaction of power and speed, power and pulse rate, power, speed and pulse rate. Then we produced surface plots from Minitab 19.1, and then these figures, the surface plots, communicate the same thing with this figure. For example, this is power and channel width. You can see that the width increases with the increase in power, but decreases with the increase in speed. The same thing applies to these other two plots. Then, by result of depth, the same thing. It increases with the increase in power and decreases with the increase in speed and increase in pulse rate. The interaction plot and the surface plots. These figures I said before, they communicate the same thing with this. And then the aspect ratio. The aspect ratio is a little tricky. It increases with the increase in power and also decreases with the increase in speed and the pulse rate. The same plots. Then heat affected zone. The main effects plot, the same effects like we saw in part 1. Increases with increase in power, decreases with increase in speed and pulse rate. Then the interaction plot and the surface plots. And then surface roughness, the same thing. Like we saw in part 1. We got these equations, the regression equations, from the response surface methodology. Using these equations, you can estimate the values of the parameters by entering the values of the input. For example, the first equation is for the width. If you know the value of power, and the value of speed, and the value of pulse rate, you can estimate the values of the width that you can find. Now, we compared the experimental results with the predicted results using those equations. And this is what we got for the Lazarus width. The black line represents the experimental values, and the red line represents the predicted values. As we can see, in all the graphs, the experimental values are close to the predicted values. Then, we did multi-objective optimization of the parameters. We got these results. The goal was to minimize surface roughness, minimize heat affected zone, maximize aspect ratio, because we need high aspect ratio, and maximize depth to get maximum aspect ratio, and then minimize width. Now, these are the optimal values we got. For power, it was 3.2273 watts, and for speed, 12.0202 millimeters per second. And the pulse rate was 1000. Then we validated the multi-objective optimization results using 3 sets of experiments. And then we got the mean value of the responses. And then we calculated the absolute percentage error using this equation. These are the results we got. As we can see, the values of absolute percentage error is very small, because the experimental values are close to the predicted values. Then we did repeatability test to find out how repeatable the values were. We conducted 10 experiments under the same condition, the optimum condition, and then we got these values of the 5 responses. Then we plotted these figures to show the repeatability of the responses. Now this line represents the mean value. This lines, the mean values of the responses that we got from the 10 experiments. Now we move to the last part 3, where we use artificial intelligence model, specifically adapting universal inference system. These are the rules that we had for Rashad width, and then these are the rules in the rule viewer. From here, if you know the value of power and the value of speed and the value of pulse rate, you can enter these values in the system, and you will be able to get the estimated value of the width. And then this is the structure of the amphis for width. Then this is the training error, which did not exceed 1.1. And then this is the plot of the training data against the predicted values under the same condition. I said we used 70% of the data for training, and then 30% for testing. And this is the plot of the testing data with the predicted values. Now, we compared the experimental values with the predicted values. Again, we got similar results like we got for response surface methodology. As we can see, the black line again represents the experimental values, and the red lines represents the predicted values. They are very close, as we can see. Then, we plotted this graph to show how close the experimental results were to the predicted values. These are the predicted values, and these are the experimental values. We were able to get the line of best fit, cutting across all the values. This one, this small square, represents the predicted value, like this one. They are overlapping at some point. So this one is the experimental value. So the line of best fit is cutting across all the values. This shows the high accuracy of the models that we developed. And then we produced surface plots. These are for Magusano relief, like we did with the response surface methodology. Then for the Magusano depth, we did the same thing. These are the rules in the rule editor. These are the rules in the rule viewer. Again, you can be able to estimate the values of the depth by entering any set of values of power, speed, and pulse rate. For example, for this one, at power of 3 watts, speed 50 millimeters per second, and pulse rate 900 pulses per inch, you get 178 micrometers, the value of the depth from the system, from the model. Then, this is the structure of the model for depth, the training error, and the comparison of the values of the training data, the experimental values and the predicted values. The 30% of the data used for checking, this graph compares the values of the 30% data and the predicted values. We compare the experimental values and the predicted values again. Again, we see that the values are very similar. They are so close. And similar graph like we got for width. Again, showing high accuracy of the model for depth. We did the same thing for aspect ratio. And we were able to also compare the predicted values and the experimental values. Similar, like we did for depth and width. We did the same thing for heat affected zone. The rules in the rule editor, in the rule viewer, the structure of the model, the training error, and the comparison of the training data and the predicted values, and the checking data and the predicted values. We also compared. Then we compared the experimental values and the predicted values. Still very, very close. The values are very close. And then the same plot, the line of best fit crosses all the values, which indicates high accuracy of the values and the model. Then the last one, the surface roughness. We did the same thing. The rules, the 27 rules in the rule editor. The 27 rules in the rule viewer. We can estimate the values of surface roughness by simply entering the value of power, speed, and pulse rate, any combination in the model, and you will get the value of the surface roughness. The structure of the model and the training error. And again, we compare the training data with the predicted values. We did the same thing for the checking data. And then we compare the experimental values and the predicted values. Again, they are very close. Then we plotted this graph again. The line of best fit crosses most of the values. Then, of course, we got the surface plots like we did with the response surface methodology. What conclusions do we draw from this work? Number one, we got better metal channels with the quantum samples, as we saw. Number two, smaller values of width, depth, and surface roughness and heat affected zone can be obtained with coating. But when you coat, you get higher values of aspect ratio, which is what we decided. The width, depth, heat affected zone, and surface roughness increase with the increase in power, and the decrease in both speed and path spread. The aspect ratio increases with the increase in power, but decreases with the decrease in both speed and path spread. Now, when we optimize with response surface methodology, we got that power is the most significant factor, followed by speed and path spread, which is in line with the study done by Mohammed and others, as we saw. They got the same one. And then, the interactions among the inputs affect the values of the response. For example, we saw in the interaction plots, power interacting with speed affects the values of the responses for all the responses. And then, the regression models have high accuracy. Those equations that we saw under response surface methodology, we saw that the models have high accuracy from the plots we saw, and the predicted values compared with the experimental values, they were so close. Then low power with high speed and high pulse rate lead to good results due to low thermal damages that appear in the ablation zone. Then, the adaptive universal inference system models have high accuracy. They can be applied to examine other optimization models for CO2 laser micromachining of PMMA, our material. The ultimate conclusion is that coating PMMA with 99.95% pure aluminum improves the quality of the microchannels fabricated on the PMMA substrates. And then what contributions did we make in this field? We were able to investigate the effects of power, speed, and path spread, and coating PMMA with 99.95% pure aluminum. I never found in literature anyone who had done this. Then we also developed statistical models with response surface methodology, and we found the optimal conditions. We performed ANOVA to examine the significance of each input. And then finally, we developed highly accurate models using adaptive universal inference system. And the models were examined and validated as we saw. And they can be used to assess other optimization models. And then, what next? We did not do everything, so a lot more work has to be done. So what should be done beyond this? Number one, future studies should consider other inputs, like the startup distance, pulse width, air pressure, and others that we did not consider. Future studies should also consider other responses that we did not consider, like the bar width, dimensional deviation, and bar height, among others. Future studies should also consider other shapes of the microchannels, like trapezoidal, snake shape, and circular shapes. We consider rectangular shape only. Then, future studies should also fabricate other materials, ceramics, composites, metals, and other polymers, like polycarbonates, PET, and PDMS, that we did not consider. And then, future studies should also consider different coating materials, like chromium, silver, and gold, which we did not use. And then, microchannels should be fabricated using varying number of laser passes. We use only one. And then, 3D finite element modeling of the process should be done in future studies. We did not do that because it was not in the scope. Now, future studies should also consider higher values of power and speed and lower values of path spread. Our maximum value of power was 7.5 and maximum speed was 30 millimeters per second. So, future studies should consider higher values of power and lower values of path spread. We were fixing path spread for part 1 at 1,000. And for part 2, we varied 800 nanometer and 1,000 pulses per inch. We got some applications. Now these two, the last two are still under review. And then this is a very interesting statement that you need to never forget. Very interesting statement. The global microfluidics market size reached about $20.9 billion in 2021. And is projected to reach $52.4 billion by 2027. This is not my statement. It is not according to John. According to who? It's according to the International Market Analysis Research and Consulting 2022. It is said, no matter how good a dancer you are, you must give a step to others. Thank you very much.
So from what you have, from the results you had from the PME and the optimization, can you optimize any reduction in thickness? Let's say from what you have right now, can you use it to optimize any reduction in thickness or any increase in thickness? Use the result you have, the optimized result you have now, to optimize the result or parameters, input parameters, and also predict the output you get by increasing or decreasing your thickness of the material you are using.
Thickness of the sample?
Yes, thickness of the sample.
How do you optimize the thickness of the sample?
No,
It's fixed.
the thickness is fixed, but now you have a result from 6 millimeters. Okay, so now can you say from what you are having now, you can just tweak it?
Oh, for other thickness? Yes, because we use the 3 millimeters also. Similar.
That's what I have for now. The rest.
We started with 3 millimeters, then we changed to 6 millimeters.
From the fabrication, right? We used the and we quoted pure aluminum. 1%. Sorry, 1%. So my question is that based on the laser past, was it actually a focus or a defocus since you already put it? Did you use just the focus laser or
Focus.
the focus? So using the focus method, that is why together with the project resulted in smooth channels.
Yeah.
So since you did not do that, let me just ask. So had you been used the focus? How the focus laser, like how is it going to look like? Can the focus laser be applied on this?
Yes, it can be applied. It has been done before.
Focus?
Yeah, it has been done before. But not with the method.
Yes, I have a question regarding having very accurate hydro channels without PMMA. Where is it applied? What is the final product application?
Okay, from this is chemical application. Now, if you have gone to hospital for blood testing, you see that when your blood samples were taken, they were put in some other channels. Now, that PCR testing device can be made using this. So the work is just to create that microchannel where the fluid is passing. Because if it is not made properly, you can turn out to be positive and negative, just because of the microchannel which is not properly made. That is why this multi-billion industry, many people are doing a lot of research about it. The next question.
How many experiments do you use in handfist model?
We use the same results for the response service methodology 54.
54 experiments. You use this 54 in building and training the handfist model also. Okay, you didn't do the design of experiment before you going to handfist model. Am I right?
We used response service methodology design experiment before we went to handfist. So we used
how many experiments?
54.
54. After design the experiments, you got 54.
Yes, there were 18. We replicated 3 times to get 54.
Yeah.
In
So
the design,
54 including the replication 3 times.
Yes.
Okay, so the other thing, can you bring just one of the 3D figures of the handfist model? Any shape, any form, for any output.
This one?
Yeah, okay. Zoom. Sorry, I think I can just zoom out, zoom in. As can be seen here, the three 3D models, it doesn't have a thin precise results from the ANFIS model along with response surface methodology. Because response surface methodology giving you an equation. If you go to Al-Bab analysis, you get an equation. This equation may be second degree, third degree, any equations. So the equation can express the form of the shape of the trend of the relationship between input and output. But here in ANFIS, we don't have any clear trend. So how could we get the same result from these two methods? I think there is something wrong.
The reason here is simple. Because the numbers,
As you can see, the speed, when the speed increases, the heat affected zone increases until the middle point. After that, it decreases again. But after you go to the pulse rate or the other parameter at the middle point, it's totally the curve change, it becomes a straight line.
this is because of one reason. Because we have only 54 experiments. We needed more to get the trend here for ANFIS. If we had like,
I'm just wondering, how could you get this result along with the same result, the same precise results you get from the response services? It's supposed to be a totally different process if you compare both of them. For example, okay, let's speak in numbers. If you put it in the ANFIS model, number 15 in speed and number 9 in the pulse rate, you will get a heat frequency, another number.
yeah.
Okay? If you put the same values in the response surface methodology equation, then you will get the same number, I think.
Not the same, but close. Not the exact number, no.
Because I think your error is very small. Also, your improvement is very high. I think it's not logical to get that 84% improvement in the aspect ratio and 44 and 24 improvement in the heat affected zone. This number is a very big number.
You mean the improvement due to the layer?
When he used, for example, underwater and compared it with the air conditions, he got improved cutting conditions from in underwater. The improvement percent around 24. It's a very big number.
It depends on the application. Sorry, it depends on the application.
Maybe in
for
the
laser,
microscope it's different.
For laser abrasion, okay, most the width is due to the heat.
Okay.
Okay, so if you eliminate the heat, I think more than 50% of the effect. So if you put something, eliminate heat, so at least you eliminate or improve like more than 50%. So this depends on the application and reason. And also, the nature of aluminium as a metal completely differs than PMMA. So existing of metal reduce the heat effect, and also I think how we can say make the beam very concise. Okay, so it improves very much the diameter of cutting, and this reflects on the aspect ratio. So it affects, by the way, it affects the diameter, I mean the width, and also due to concentration go deep. So you work on both sides, on the diameter and also on depth. Okay, so if you divide both, improvement give you like a very good aspect ratio. This is the reason.
Okay.
Yeah.
Can I say the three applications?
No.
You have three applications. Can I see the three applications? I will see the journal's names. Actually, you did a very good work. It's a nice work. I have a lot of experiments. How could you finish all of this work in just this in master degree? How could you finish this work in master degree? He did a lot of work.
Yeah, there are a lot of work.
Yes.
A caterpillar, man. Caterpillar.
Also, three applications too much.
Yes, this is by the way, this is a minimum. He can do more. Yeah.
The first one, ASME 2020. Okay, it's a nice place. second one in laser. So still under review and still not under review. Okay, you just published one.
Yeah.
You have one acceptance.
These two, I sent back the revised version.
Okay. Did you write any code using in MATLAB or just use the toolbox?
No, we just applied. The work is not really about code, but we just applied ANFIS.
Just use the toolbox to apply ANFIS in your results.
Yeah.
Okay. So how could you input the 45 experiment in ANFIS? Can you tell us the way you use the 54 experiment in ANFIS? Because I see the rules. You show us the rules. You have 27 rules. If you have 54 experiments, how could you put 54 experiments to get just 27 rules?
The rules
supposed to have 54 rules also.
No.
So how could you make
the rules are generated automatically? The rules are generated automatically by the system.
So if you generate the rules automatically, okay, I got you.
There's nothing I can do to increase the number of rules. I just put the 54 experiments and you get the rules. It's automatic.
If you generate the rules automatically, so you didn't use the 54 experiment. You just use 3 levels for each parameter.
I said 70% was used for training and 30% was used for checking. We divided the data into two.
Okay, you make it like a weight, a weight person. It's very good.
And then one output at a time.
Use the fuzzy logic toolbox.
Yeah.
Not coded.
Yes.
Thank you very much. Any other question?
Last question.
One last question. Last question here. Okay.
The 18 experiments to be said replicated in 3 times. Was it at the same experiment, the same setup, on the same substrate, or 3 different substrates?
That means at let's say 3 watts, 15 millimeters per second, and 1,000 pulses per inch, we did 3 experiments at the same time.
The same time, the same substrate.
Same.
Okay.
Thank you very much.